and because of that, hang on, there are these challenges you have to work with, and yet, despite all of the complicated nature of the problem, you still have to give, at the end of the day, practical advice. And the question we wanted to get to is how could we set up a system where we could do that for malaria? And I'm going to talk about the steps that we went through in some detail to get there. And this is in two projects that I've done in collaboration, one with the Uganda National Ministry of Health and a team under Dr. John Reck, as a friend of mine, a very good friend of mine, who's working there, leads the team. And the other one is the Bioko Island Malaria Elimination Program, which is much closer to where you are in Nigeria, just a little south of you, in fact. And these are two programs where we're actually implementing these principles. And you can see, if you look at my CV, you'll see some published papers and things like that. So I want to go back to the start of all of this. Is a guy named Ronald Ross. In 1897, Ross became famous for being the first person to see malaria parasites in a mosquito gut under a microscope. This is 1897. For this, he got a Nobel Prize and fame and many, many things. But that was what launched his fame. In the years that followed, Ronald Ross decided he wanted to devote his life to the extermination of malaria. And so he wrote a paper in 1899 about the extermination of malaria, and he set off to Sierra Leone to set up a research center. And for the next 10 years or so, 12 years until 1911, Ross was focused on the prevention of malaria. How is my sound? Can I just say, are you hearing me okay?
Yes.
Give me thumbs up if it's okay, or thumbs down if it's not okay. Oh, good. Oh, yeah, I'm seeing mostly thumbs up. That's good. So Ross, in designing these systems to manage malaria, a lot of attention to the measurement of malaria. So there's a problem of measuring malaria. So many of you probably unaware that Ross was also the person who introduced the thick film into malaria in 1903. So this is one of the standard techniques that we have for diagnosing malaria. And I won't argue that it's the best, but it is certainly, it was an indicator of what he was interested in. Now, one of the things that Ross did was he introduced dynamical systems as a tool for thinking about malaria as a complex system. And this is from his 1911 paper. Manuel, are you there?
Yeah, we're not hearing at the time. We're no longer hearing you. You said Ross was the one that introduced what?
Dynamical systems.
Okay.
Okay, is my I hope this is working. It's always working about technology across continents.
It's fine now.
It's remarkable that we can do this at all. So let's celebrate that, right? Okay, so in 1911, this is from his Nature paper. Actually, the first mathematical model of malaria at all was in 1905, and it was about larval source management. The second paper was about malaria transmissions in 1908 in the report on the prevention of malaria. Hang on just a sec if you can. Amy? Just a second, will you? Amy? Amy? Would it be possible? Wow, it's too loud. Thanks, sorry. I'm back. Sorry, there was some background noise that was getting distracting. So the next thing Ross did was starting about 1915, this is one of the last chapters of Ross's academic life, he set out to develop a system for using mathematical models to understand epidemics that he called a priori pathometry. Now, in 1916, he kind of laid out what he thought was a rationale. He starts out by saying it is somewhat surprising that so little mathematical work should have been done on the subject of epidemics. And then after a few paragraphs of introducing the problem, he says the whole problem is subject to two methods, big approaches. One is what we would call today statistics, and the other one is what we would call dynamical systems. And he argued that these two methods ought to come together in the middle around the truth. So that's kind of the approach that we're taking in adaptive malaria control. And that's the idea, is that you have to go back and forth between conventional statistical approaches and mathematical approaches to get close to the truth that you want to get to. Now, to go on with this theme a little bit more, by 1923, papers were being written like this one that had all of the elements of what I would call core research metrics. So the prevalence of malaria by age, which you can see plotted here for two different sites in Senegal. So, and you're actually seeing denominators on this. I love this graph because it's actually got the data right there on it. So if you want to pull it down and look at it, and what you're seeing is, prevalence rises quite quickly after birth with respect to age and reaches a kind of a plateau, or at least it did in kids older than 2 and younger than 10. So we know now the parasite rate, I'm going to call it continued parasite rate, they meant the number positive divided by the number examined. We would call this prevalence today, or parasite rate. It has stuck around as a kind of a term of trade. It differs by age, by sex, by diagnostic, and by time of year. I should also say by location, because it matters a lot what's happening with the local populations. The second metric was something that we call now the entomological inoculation rate, which is essentially an estimated number of infectious bites received by a person in a day. So this varies by age, by season, by location. And we collect it, we take the product of two metrics that we've collected in the field, the human biting rate, the number of bites per person per day, and the sporozoite rate, fraction with sporozoites in their salivary glands. And we take that product and it's called the entomological inoculation rate. The third one you can actually see is the force of infection. It has to do with the rate at which prevalence rises with respect to age early in life. So it's the number of infections per susceptible person per day. And you can read it off this slide by just looking at that slope early in life. So these are our metrics that we use today in malaria. Now, the flip side of this is that mathematicians have gone around trying to understand various aspects of malaria. And you can now understand malaria today. This is a graph we put. Oh, and I should mention, whenever you see a QR code in the talk, it's linking out to a paper that we've written somewhere. And if you just take your phone and scan it and then hit the button, it'll take you there. So these are two papers on the right that have QR codes that take you to papers we've written about this. So the one on the bottom is actually a systematic review of mathematical models that is now dated. It's more than 10 years old. By our estimate, now more than half the models have been published since it was published. And in the top right, we lay out a kind of a vision. So anyway, in this second paper, we noticed that malaria models look like this. There's a human part, mosquito part. There's some assumption about how human mosquitoes meet up through blood meals, and spatial dynamics is included here. And on the left-hand side, you have a part that's often neglected, which is mosquito aquatic ecology. And they're connected by these various points: egg laying and emergence on the left, blood feeding on the right. Now, the key about this is that there are nonlinear aspects of these interactions. So as you increase transmission intensity over time or throughout the year or from place to place, you find that there are these very complicated nonlinear dynamics, including blood feeding, which is an interaction between humans and mosquitoes, malaria immunity, and parasite outcrossing, 3 examples of nonlinearities. Now, in addition, as we look at these systems, they are exogenously forced by weather, by vector control. So in some ways, we're considering this to be a system with 4 interaction agents. There are humans, there are mosquitoes, there are the parasites that are transmitted through blood feeding, which we call transmission dynamics, and there are malaria managers who go out and do things. They do vector control, and they introduce interventions through the health system or using therapeutics. And all of this sort of leads to these very important, complex, long-term interactions through the evolution of resistance. And then the systems are changing with health, behavior, and socioeconomic development. So you see we have these very complicated situations. And if this is really a complex adaptive system, then we need some kind of way of dealing with that because our standard statistical methods are going to break down. If we try to apply something we learned there to something here, it's not going to work. And I'm just realizing I cannot see a clock. Okay. Oh, I was going to walk you through that. The other problem we have with malaria is this quote. It's exemplified by this quote by an early century malariologist named Lewis Hackett working in Italy. And Hackett was sort of a crazy entomologist who was out there sort of looking at the way things work very close up in the field. And he particularly was interested in the problems of sort of vector control. And he wrote this. He said, malaria is so molded and altered by local conditions that it becomes 1,000 different puzzles, like a chess game, right? So you have these very simple starting conditions, and they recombine in various ways to give you, so you can basically say, what does the system look like, but you don't know what it looks like here. That is to say, there might be some unique features of what malaria looks like, and these are the problems, these are the challenges. We have a complex adaptive system, and it's locally peculiar, if I can say that. Peculiar meaning in each place it has some features that are unique. And so we set out to develop a system that allows us to deal with this. So ultimately, it is a management system, and it's important for us to say that. This is about managing malaria. So we have to be cognizant of the malaria managers and their needs. But also, it's trying to sort of deal with some of these big problems. And so this was the system, I'm going to talk a lot about the system we developed for the Uganda Ministry of Health, which is a national level system where we have essentially 146, it's a population of about 48 million people. We have about 146 management units called health districts there. And each one of those health districts is about the size of one Bioko Island. So Bioko Island Malaria Elimination Project is the other program we've worked with. That's a one island. And so 140, each one of the districts represents more or less the same, is equivalent to one Bioko Island. And so there are different problems that come up, and I'll talk about some of those. So to do this, there are these common elements that if you want to do management malaria, you want to use evidence in a routine basis to manage malaria, you need to do a few things, and you can't really get around it. So one is you have to have these stable data systems and data curation. You need to establish a whole ecosystem for doing analytics. That is to say, you have to have conventional analytics in place, and you have to have simulation-based analytics in place to be able to deal with both of the problems, or a lot of the problems you have. And they have to be streamlined because these are very complex computational environments, and they have to be integrated so that they work together. And there used to be this game I played as a kid called Mousetrap, which was like a good big Rube Goldberg machine where, you shoot a basketball, it hits a skateboard, it triggers a marble machine, and lots of crazy things happen in a big domino machine. And that thing has to be coordinated so it all works alike. Now, a couple of things about this is if we're doing this for a malaria program, we wanted to set some professional standards for ourselves so that all of the things that we do are transparent and replicable. That is to say, we don't want to do anything that nobody can't look inside with as much rigor as they want to. Now, we have this problem of adaptive malaria control. So what is it? It's an iterative process. So that was the essential idea we got from adaptive management, is you have to have an iterative process. So over and over again, you're looking and re-looking at the data. And the problem here is that you're expecting to be learning about the system over time, and the amount of uncertainty about future decisions to be reduced on average over time. That's probably not true, but I'll talk, if I get a chance, I'll talk about why. But we needed a way of storing information, and it needed to be not just storing information in my head, but storing information institutionally. So we needed a way of generating a kind of a memory about this and versioning for the system. And finally, there had to be some ability to communicate everything that we're doing, because the people who do analytics need to be able to tell the people who make decisions what they found. And so that's the one part, is we needed a platform. And on the other hand, we needed a bunch of analysts. So we started out, as I mentioned, in Uganda. We formed a team around John Reck. And we encountered some other problems. So there's this, I've talked a bit about malaria as a management problem. What exactly is a professional malaria analyst? Is there a thing? And we couldn't find anyone who'd sort of set up training programs for it. I mean, there are people who have done things, but by malaria analytics, I don't mean research, and I'll get into this in a minute. I mean somebody who's actually trained to take data and turn it into policy advice, not somebody who's trained to write academic papers. So we had to sort of establish what we thought we meant by that. And then all of the people who were going to be professional malaria analysts needed a career track. So in the case of malaria in Uganda, we actually established the malaria now I forget what it's called, MARP. Anyway, we developed a center. I'm flustered, sorry. But REC actually formed this at the Uganda National Institutes of Public Health. So we now have an institute that can actually create a career track and help people to get grants and manage money to do malaria analytics. We needed training and documentation. We needed, and most of all, sort of very importantly, if we're going to be doing malaria analysis or malaria analytics, and the endpoint is to give policy advice, we needed an inferential framework for doing that, because it's not the same thing as doing science. And so we needed to define adaptive malaria control as a methodology, and we needed to sort of then start to put this out in peer review so people could look at it. So that was our big picture of what adaptive malaria control meant. So the rest of this talk, I'm going to talk about bits and pieces of that, of this thing that we've assembled as this methodology, if you will. And I'm going to give you what I think are some of the highlights of it without going into the technical, boring details. The first is, as I said before, this is a problem about managing malaria. It's an analytics versus policy, or an analytics and policy versus scientific research. So what makes it different? So what are we doing? The first thing is we're trying to set a lot of what we do with models is we try to set rational expectations, so that when people are making decisions and trying to set coverage targets, or they're trying to set expectations about the way the program is going to respond and set goals over time, so strategic planning, that there's a framework for doing this, and there's a set of options that they can do. Turn to vector control, they can do nets, indoor residual spraying, larval source management, attractive toxic sugar baits for environmental management. Through the health system, there are various ways there's the core intervention is case management. There's chemoprotection or chemoprophylaxis, if you give people drugs on purpose to create this period of chemoprotection, they call it chemoprophylaxis. There's intermittent preventive therapy, mass treatment, and now we have vaccines. So the question is, if you have so many options, which are the best ones to use, when, where, and why? Now, when we sat down with Jimmy in his office, Jimmy Opigo is the director of the Uganda National Malaria Control Division. Now they've changed the name to Uganda Malaria Elimination Division. We sort of had this view of malaria with three components. There's a past, where we do all of our analysis. So all of our data describes the past. None of the data that we have describes the future. That would be great, right? We need a DeLorean so we can go back and get data about the future so we can make better decisions. No, we don't get to do that. So all of the analysis we do is in the past, and we use that to make an assessment of the present. So what's happening now, based on what I've learned in the past, and what can I expect in the future? So each one of these activities involves different activities: statistical analysis, model fitting, estimation. So we can do something like nowcasting or outbreak identification, and in the future, forecasting, simulation, and optimization. And these are linked to very specific programmatic needs: monitoring and evaluation, estimating the burden and averted burden, and so on. So this is what, when we sort of talk about a pipeline for doing analytics, we need all of these components all at once to be working in harmony. In the middle of this, there's this concept that I'm going to harp on. I think it's a critical one. I'm going to call it malaria intelligence. By malaria intelligence, I mean something very specific. I mean that we need to take the data we get and we need to generate the data we wish we had. So you never get the data exactly that you want, but you need certain kinds of data to be able to make decisions about the future, and that's what we're going to try to do through this concept of malaria intelligence. I'll try to make that more clear, and I wish we were in face-to-face so you could ask questions about it, but essentially, if you want to think about it in this way, there's data, which we collect. After some analysis, we give, the data gets imbued with meaning through analysis, and we call that information. Malaria intelligence is the information that we need to make decisions. So we have to sort of design our systems to create these outputs, and I'll show you exactly what I mean. There's one core algorithm. And now I want to talk about this just a little bit more, and I'm not going to have a lot of time, but analytics should not be doing the same thing as science, right? Science is involved in questions about what we know. Policy is about what we should do. In science, we try to isolate phenomena and design experiments with simple and clear outcomes. And in policy, we're trying to integrate evidence in synthetic frameworks. In science, we should wait for strong evidence, but in policy, you're better off giving an answer now based on the crappiest of answers, the crappiest of evidence, even if it's weak, right? We want to use the best evidence, even if it's weak. That's a nicer way to say it. And in science, we sort of wait centuries or decades and things change incrementally. In policy, though, giving a bad answer isn't always bad. Or giving an answer based on weak evidence isn't always bad if you can use your interventions to learn the thing that you wish you knew, right? Because you're constantly taking action in this iterative framework. So you're going to learn about malaria through surveillance, monitoring, and evaluation, and so on and so forth, right? So in this big scene, the big topics that we're talking about are things like the global burden of malaria. So burden is a term of trade that means something very specific: years of lost life, years lost to disability. And in malaria, these plug into these big systems for estimating that. This is some work I've done over years with the Malaria Atlas Project. And you're seeing this little guy on the left is a hippo, as you know. This is in honor of an old friend of mine named Joel Bremen, who is, many of you will be aware of him. He was on the first Ebola outbreak, and he sat in the office next to me, and he was my neighbor across the street for years. And he wrote an essay about malaria called The Ears of the Hippo. And the idea is that, the thing we see and we call malaria in the clinic is just the ears of a much larger problem. And essentially that malaria, fever, and there are bigger problems. I'll go into this in a minute. But if you need to do this, then you have to figure out the distribution of malaria by site. And you remember what I've said. So the Malaria Atlas Project is one way that I've sort of contributed to this problem of understanding the distribution of malaria. Now, the second thing is that we're trying to reduce the burden of malaria as quickly as we can, meanwhile setting the stage for malaria elimination and global eradication. And the thing I want to say about this is that we have a situation where malaria's geographical range has been contracting over the last century. So a lot of the things that you hear, for example, about global warming were really focused on the wrong thing. Within Africa, we still have a lot of malaria. So let's not worry about the expanding range. And by the way, that's another talk I'm not going to spend a lot of time on. Only to say this, that when you look at the history of malaria, that there's this strong indication that once malaria goes away, that it's very rare for it to come back. So this is one of those reasons why we sort of need mathematics. And the mathematics can be there to provide us some critical metaphors or to provide rigor to our thinking. So this paper here, and if you click on this, is a paper we wrote in Philosophical Transactions of the Royal Society of London, where we propose a hypothesis for sort of the two paths of malaria. One of these is a path where malaria nearly was eliminated. Funding went away and it was resurgent. So there's a malaria resurgence paper that we wrote. Justin Cohen led that, now with Clinton Health Access Initiative. And the other paper is, or the other pair of papers, so there was a Sisyphus paper that we published discussing the history of malaria in Zanzibar, which had malaria control, no malaria, malaria control went away, malaria came back. And it's this problem that if you do malaria control, you can make malaria go away. But if you don't actually kill the beast, you don't go all the way to the end point of eliminating malaria, what does that mean? Then malaria keeps coming back. But that ignores the other future, that if you do go all the way to the point where you certified malaria elimination, it doesn't come back on a regular basis. So what I'm showing you on the right-hand side is some data from countries across the world that have eliminated malaria, that used to have it. And you're seeing the white dots are lots of malaria cases acquired during travel with no knock-on transmission. There were no onward transmission. The yellow and red represent varying degrees of outbreaks. And what you're seeing here is that a lot of the countries that achieved malaria elimination remain malaria-free. And that's a pretty, it's not the story that you're hearing from most people when they talk about, oh, the dangers of malaria. No, it's really a real thing, and there's no good reason for it that we understand in the math. So this is one of the attempts we've made to try and answer the question, why is malaria elimination a stable state, or why has it appeared to be a stable state? And there are lots of really good reasons, but if you're going to try to make malaria policy, you need to have history as your guide as well as everything else, so you remember what can be done and what has been done in the past. Now, what do I mean by robust analytics? So if we're going to be giving out advice based on weak evidence, we all admit that that's a tenuous kind of thing. It's a risky thing. We need to be able to do this with some rigor and confidence. So I developed this phrase and I started using it called robust analytics for malaria policy. What do I mean by robust analytics? What I mean is that we're going to do policy that goes to great lengths to characterize, quantify uncertainty in our systems, and then to fully propagate that uncertainty through the analysis that we're doing. That is the essence of what I mean by robust analytics. And we're going to dispense at the end of this robust policy advice. So advice that's robust is, I don't mean that it's, we're not inventing a crystal ball and we're not giving strong advice. What I mean is we've thoroughly looked at the situation and our advice wouldn't change if we had done the analysis in another reasonable way. And the reason is because we've already tried most of the reasonable ways. That's how we can be confident that it won't change. So the idea here is you don't want to just do the analysis once, you want to do it multiple times. Make clear recommendations, discuss alternatives, and then identify the information that would help you discriminate among alternatives. That's what I mean by robust advice. So how do we generate robust advice? How do we do robust analytics for malaria policy? Well, a lot of it comes back to using the data we have to best effect, right? I've said it's weak data, and I need to make this clear that I don't want to sort of, I pointed out that we have these core research metrics, but there's a big problem with the core research metrics is if you want to use data and you only want to restrict yourself to core research metrics, that you don't have research projects going on everywhere. If you're making decisions about malaria, and in this case, malaria in Uganda, you need evidence describing malaria in every place that you manage, in all 146 districts, right? And so what I'm showing you is a district where I've worked for years as a part of a research team, Tororo district in red. So it's very specific districts with their own histories and locations. This is a place where we have lots of research data, but a lot of places don't. And so we need a way of sort of describing malaria everywhere. Where are we going to get the data? Well, the answer is, there's only one answer, because there's only one set of data. We're going to get it from the health clinics. Now, that means we have to use data, surveillance data, that many of us have been trained to turn our nose up at, because it's a passive study design. There are all kinds of problems. If you go to specific clinics, you can sort of tell stories about how terrible the data are and all that kind of stuff. But remember, what we're going to do is we're going to develop this platform for developing malaria intelligence. So we're going to take that data, warts and all, and we're going to turn it into data we know how to handle in a research context. That's essentially the element. So even if we don't have data, we have a prediction of a research, one of these core metrics, and I mean prevalence of malaria, that we can apply to every place. I also mean the EIR. And so what we've done is we've generated these algorithms, and I'm not going to go into detail. I'll tell you some of the details, but where we sort of pull the data out of HMIS through these data systems, they get updated on a regular basis, and then we fit models to the data, and we run these other algorithms to generate estimated PR. I will talk about that. And then we estimate PR, EIR, and we have this suites of models that we've fitted to the data that we can now start using. Now, for this to happen, we have to have these well-developed data processing pipelines. The core concept here are a change data capture algorithm that queries DHIS2, looks for changes, updates a raw database. It has version control. So if an observation changes, you version that observation with a new one. And then there's some processes for automatically identifying outliers, removing the outliers, imputing missing values and outlier values, doing some standard consistency checks, and generating a clean data. So this happens now behind the scenes in Uganda. It's been happening with our team, and we are now in the process of integrating it back into the Department of Health Information. Oh yes, I should have said, in our process of collaborating with the Ministry of Health, we have now started working very closely with the people who maintain the databases. In this case, it's Department of Health Information. And I will say on the Bioko Island thing, where Bioko Island is run on oil money, so there's a well-funded project that actually does all of this in a different way, with much more sort of sophisticated software and things like that, and different set of problems. But there is the same problem when we have this sort of updating of the data that has to be done on a routine basis. Now, I've said this before, I'm going to say it again. Malaria surveillance data is highly suspect. What we want to know about is malaria. What's happening out there? If we went and measured it out there, what would we find? We don't get that. We get malaria prevalence. Or sorry, we get a statistic we mean what we call the test positivity rate, which highly suspect unless you're testing almost everyone. But if you are testing everyone, it starts to get better. There are all kinds of other problems. So what we wanted to know is, could we use the test positivity rate from over 6,000 facilities in Uganda to predict the prevalence of malaria? So on the one hand, we collected all the malaria prevalence data, matched it to time and place. And on the other hand, we sort of got all our clean TPR data, and we sort of then did a statistical study with covariates. In this case, our most important covariate was also from the DHIS2 as an indicator of how much severe malaria we had, and which ended up being a very important correction term. And once you put that into the model, then you actually do a pretty good job of predicting prevalence in a place. Now, this is given the fact that malaria prevalence is highly heterogeneous if you go out there. And not only is it heterogeneous, they don't tell us exactly where they did the study. So we don't know exactly where the data were collected in many of these, in the sort of DHS and MIS studies. They jitter the data. So we don't actually know. And despite that, we're doing a pretty good job. What I'm showing you on the left-hand side is predicted PFPR, and I'm showing you on the right-hand side observed. And now we've used this and transformed it into time series of PFPR. So this is, for example, one district on the right in Uganda, Madiokolo district up in West Nile, they call it. And what you're seeing is a seasonal pattern of PFPR. You're seeing interannual variability that's been fitted to this. You're seeing the timing of interventions. The red vertical lines are ITN distributions. And then you're seeing, in this case, there was one towards the end of the, very recently, we started doing indoor residual spraying in Madiokolo district. So here is now an algorithm that we take all of this. So the malaria intelligence systems look something like this. It's a very busy slide, I apologize. But we start with these databases at the top, these dark blue cylinders, and we develop these algorithms. This is our mousetrap. And you're seeing the boxes are sort of data assets that we've created, your digital objects. we're using the term data very fluidly. So every one of these boxes is an object, and every sort of arrow is an algorithm. And so we have these algorithms that sort of maintain spatial hierarchies, or sorry, spatial a location table, all the and shape files. So all of the things we would need to generate clean-looking communications products and to do a clean analysis all the way down through linking up with simulation-based analytics. So now we're using mathematical models. And the core is that algorithm I just showed you is what links the surveillance data to the research data. And on the right-hand side of this, I've put this one arrow, adaptive sampling. So we do make predictions about what prevalence would be in every location by age, by sex, by time of year, by diagnostic. And that is verifiable data that we can sort of use to test how well we're doing. So that's the point of all of this, is not to sort of publish papers. We want to know how accurate our systems are. And so we have all of these things that we do to check. So at the end of this, we also have a calibrated swarm of mathematical models, which I haven't talked about. Let me go back and talk about that now. Oh, sorry, more about platform. So what does the platform actually look like? On the one hand, we have all these GitHub R packages. For every data asset or digital object, there's a corresponding R package where the code is, version controlled code is available and anyone can examine it. It's supposed to be well documented. And then on the right-hand side, we have a companion set of objects, sort of programs that are R packages that do simulation and some of our analytics. And we also have these deep dives that allow us to sort of take a sort of a look at some of the parts of malaria. So this is like now delving into something that would be more academic. And all of these data that we generate live in a place that we call box or ramp. It's a ramp directory under our box account that's secure. And then we have these websites that we generated. So you're looking at two of the websites. The lower left is one that it discusses the methods. I would show you the links, but these things, we've been developing this so fast. You know, it'd be like walking into a house expecting to live in it and only realizing the construction team is still there, and that there's a lot of work going on. You can't live in the house yet. So that's the websites are there and up and running, but they're like being now filled in and as we're learning in real time about how this works. So I want to talk about simulation-based analytics, realizing that the time is sort of running out. But I want to start with this picture that we sort of we started with this. You know, mathematical models now are actually mostly in these academic papers. You can find out about them, but there are these gigantic individual-based models, comprehensive individual-based simulation models for malaria. If you look at all these models, they also have some very common elements. So the first is there's some part of the model that describes what's happening with an infection and immunity in the humans, including possibly demography and other elements of our ecology. These would also take care of drug-taking observational processes. There's some part of the model describing what's happening with the adult mosquito populations, including infection dynamics and to some extent ecology. One of the important elements of the ecology is blood feeding, because that blood feeding is what gives rise to parasite transmission from mosquito to human and human to mosquitoes. And sort of within that, we can now describe spatial dynamics. So this is Emmanuel is a co-author on this paper, and if you see the QR code in the bottom, you'll actually see the paper where we sort of lay this all out. On the other side, there's this element, the aquatic ecology, that is initiated through egg laying, and then the adults emerge and rejoin the population. So we have essentially these 5 core elements, called dynamical pieces, which come in 3 inseparable chunks. So human malaria and demography, adult ecology and transmission dynamics, and the aquatic ecology. Those are our 3 chunks. There are actually 5 processes we're describing because we're separating out the models for ecology. And demography separate from the models for the infection dynamics. And then we have these things that we add on where we do vector control and weather. So that's the basic way we would take this complicated universe of mathematical models and turn it into something that we can work with. And it looks like this. So there is a rigorous mathematical framework. I will not try to go into detail to anything you're seeing on the right. I'm just showing you that it's there. And there is a rigorous mathematical framework. Some of it is described in that paper, some of it's new. But essentially, this is, you'll see the 5 boxes with the 2 connecting bits, the blood feeding, and then adult mosquito ecology, aquatic ecology, infection in mosquitoes, human infection dynamics, and demography. And the way that we make all of this work, we've identified these interfaces, these core outputs and outputs from one part of the model that become the inputs to another part of the model. And we've rigorously defined what those have to look like, but then we've made them flexible so you can do everything you want. So we have a system that's modular, flexible, and extensible. And now essentially any mathematical model you could ever build of a mosquito-borne disease that is framed as a dynamical systems model, we can probably do it in this framework. And we can probably do emulators of some of the more complicated models. So within this, we've handled some of the big sticky problems: heterogeneous exposure, heterogeneous transmission dynamics, spatial dynamics and importation. We can add now exogenous forcing with weather and resources, vector control, and health systems. We have enforced a built-in observational processes. So if you develop a model to add to this, it has to specify how you translate the state space describing infection or ecology into an observational process. And then we also have these built-in analytics. So many of you are familiar with the concept of R naught as a threshold concept. So we actually have done the theory so we can actually output and compute threshold conditions. And what we've ended up now is we put this into software. So this is actually a pretty well-developed website. Simulation-based analytics is what I mean by SIMBA. It's also a lion, as you will know. But software for nimble model building. So if we're going to be engaged with policy makers, we're going to have to be able to sort of build models fit for purpose and change them in a very good way. And some of them are going to be simple and some of them are going to be very, very complex. So along with this complex system, we have this, actually, it's a fairly streamlined system for setting up models. And it does a good job, and you're kind of moving from the simple elements to more and more complicated elements as you move from left to right. But going through this process, you can build a model that has anything in it, and there are built-in algorithms. This framework took a long time to get going, and I'd be very interested in discussing with any of you who are mathematical modelers exactly what it does. But essentially, I don't mean that you're going to be primarily sort of making up a model from scratch. This is more of a secondary model building, if as you were, where we're taking models that somebody else has built and we're applying them to malaria programs. So that's what I mean by model building here. I don't mean in a sort of blue sky to, there are a lot of meanings to this. Now, this is where my software crashed. So some of these slides are not the ones I intended to show you, so I apologize in advance. But let me start by talking about malaria now in this modular framework with these 3 big chunks. And one of those components in the human chunk is malaria epidemiology. I'm going to call this a script X. The X component of the model is the malaria epidemiology. If we were to start with sort of Ross's description of malaria, we start with a simple exposure and infection model. Exposure is defined as a force of infection based on a very simple model, now as the way I understand now, a very simple model that translates the entomological inoculation rate into a force of infection. And there's some very simple assumptions about blood feeding and transmission, infectiousness and clearance that give us something like a very basic model to build on. Now it's wrong, but it gets some of the basics right. So the question is, how much more do we have to add? And what we want is we want a framework that sort of allows us to go all the way down, right? So we can start simple, like Ross's model. We want to be able to go as far down as we can. So this was our goal. So the next thing, of course, we want to add immunity. And the very first model was a model developed for a field study in Garki, Nigeria, where you guys are, I think. And but the models for immunity and concepts of immunity have grown since then. We also want to be able to incorporate things like heterogeneity, and we need to account for things like superinfection and parasitemia. And the next level or layer of complexity, we want to be able to take into account drug taking in response to fever and disease, but that's not all, right? Drug taking is much more complicated, especially anti-malarial drug taking. People take anti-malarial drugs when they're feeling a little off, and it may not be malaria all the time. But then you care about chemoprotection and adherence. So did I take all of my drugs? And if I did take it and cure an infection, how long did it last? And now I have these other questions that come in about seasonality and the seasonal changes in malaria prevalence and detection by different diagnostics. I have care seeking, and that leads me to my research metrics, and it also leads me to these surveillance metrics. And now I have a framework where I can measure malaria, and I care deeply, if I'm going to manage malaria, mostly about severe disease. In one sense, there's a kind of a severe disease leads to hospitalization, or it ought to lead to hospitalization and sometimes death. And that's one of the biggest, most important processes, but this is always rare and it's very difficult to study directly. So we need things that sort of predict it based on transmission, age, and other factors, and it's probably not all malaria factors. Now, malaria, if you get it a lot, it's destroying red blood cells. It's linked to anemia. Anemia is linked to other diseases and increased risk and mediation of other conditions, which is probably increasing death rates in ways that are sort of ultimately, malaria is in the causal pathway. It's one of many things probably, but at the end of the day, it's leading to more death. This is the ears of the hippo argument. And then there's this other special condition that women becoming pregnant for the first time, or getting malaria for the first time in pregnancy, tend to have very severe cases, or this is accompanied by low birth weights, and then malaria in pregnancy is a generic problem, which adds to the burden of malaria. Now, so you see, we started simple, and now we have this overwhelmingly complex picture. We need models to help us sort through all of these relationships, and even if the data aren't there to tell us what these things look like in a way that the scientists would like us to sort of listen to them tell us about, well, if the data aren't there, we still have to go ahead and make the decision. So we need to worry about uncertainty. So we went about to frame it. Oh, I left one thing out. Malaria control. If we do things like vaccination, IPTP, so on and so forth, all these kinds of things are strategies we can do to reduce malaria. In a management setting, we need to know which we're going to do. So anyway, we need these models to help guide us even about questions that are not settled science. And if we're going to do this in a robust way, we need to be able to sort of start with a framework. And so I'm going to point you to a paper that we wrote and put out in medRxiv. If you search for Dave Smith and John Henry and probabilistic synthesis, and that's what this slide was going to tell you, is how to find that paper. It's a new approach to looking at this, where our main core idea was we want to be able to frame models for malaria in a way that would allow us to sort of ask questions about, responses to control, including characterizing. And this paper was a first step. It doesn't go all the way by any means, but what we show is that if you do a lot of math and you're careful about it, you can actually develop pretty darn good models that get everything basically right and in detail right. And the models don't have to replicate everything that's happening. They can just be pretty good at approximating models, and it'd be a very good guide to help you make policy. The other one, which I did have some time to make, is mosquito ecology. So we've thought long and hard over the years about mosquito ecology as a problem. And one of the things about when you say mosquito ecology, everybody thinks whatever they think. what mosquitoes are actually doing all day is they're looking for resources to consume. So we've gone down the road of sort of taking models that describe adult mosquito feeding and egg laying and sugar feeding and all the events after emergence, and they're sort of linked to these activities that we can do with vector control that modify aspects of the mosquito feeding cycle. And we also sort of have models for habitat dynamics and population regulation. And we want to be able to, again, characterize and quantify uncertainty and propagate it through a model. So this is one of our deep dives, sort of the equivalent to our malaria epidemiology paper that I couldn't show you because my machine crashed as I was trying to make the slide. But what we've done here is we developed these models where mosquitoes are in. These are behavioral ecology models for adult mosquitoes. They're either looking for sugar, which is somewhere out there, or they're looking for water, which is somewhere out there. They're looking for blood meals. And so they're moving among these sites. And what we showed you is that if you take these models and just do them, that you get something out of the models that's not exactly what you would get if you did diffusion-based models. Now you can use diffusion models, patch-based diffusion as a kind of approximating model. Well, what I'm showing you on the left is a series of steps where we build a model, solve it, do some analysis of movement, and on the right-hand side, show you that there's an emergent property, and that's one of our sort of complex dynamical systems. What's the right word? In emergent features, if you don't know that term, it means that there's something about the individual behaviors interacting with each and the interactions that give rise to a phenomenon that's somewhat surprising, right? It's not exactly what you would expected. So in this case, I've just distributed resources to, blood feeding sites, aquatic habitats. There's a simple rule that says move, this is how mosquitoes move. And what I get out of that is, and these are randomly uniformly distributed points, I get these communities, these malaria communities that are sort of self-organized patchiness in these systems. And the simple message here is that mosquitoes do things, and in this case, what they're doing is they're leaving places that lack a resource that they need as they're searching, which when you put it in those terms, it sounds pretty obvious, right? Mosquitoes are doing complex things. So anyway, this is also up as a preprint. It's called Mosquito Dispersal in Context. And so at the end of these sort of things where we've done your normal things with malaria models, mostly with other people's malaria models, we've also sort of taken these deep dives into these processes. Now, which takes us to the last sort of core complexity is transmission. By transmission, I mean the emergent features of a system where mosquitoes are blood feeding and there's malaria immunity. This is a paper I published with some folks from, so I'm in the middle of this author list. I shouldn't take much credit. Philip Bijon was the primary on this. What you're seeing on the left is a data from a demographic health system where they've actually followed people for more than a decade in this very well-organized health system. They track people to their homes. And what they found from doing a study like this is that malaria distribution is really, really almost fractile, like when you go and look at it. So you're looking at these places, each dot is a household. A blue household is one where most of the people didn't have malaria when they showed up at the clinic with a fever, and the red ones were sites where they almost always had malaria when they showed up at the clinic with a fever. And you can see the red and blue sites are right next to each other at a very, very small spatial scale. So there's fine grained heterogeneity in malaria distributions. And this is the process we're trying to define through transmission. So the question is, what if we go ahead and we just make some assumptions about transmission being well mixed at the level of a district in Uganda? Are we going to get the answer right about how it's going to respond to control? I don't think so. And so one of the things that we need to do about setting expectations is to make sure we build models where we handle things like heterogeneous transmission and get the scaling relationships right. I have run out of time. I'm right at the end, where I could take you through robust analytics for malaria policy, but let me just do this. What we did is sort of set up a system. And we're going to take that system and all of the pieces and put it together in these pipelines, these analytic pipelines, so we can run things over and over again. So each one of these things is a process that now works, and we can actually take this sort of from pull data from DHIS2, transform it into an updated assessment of malaria prevalence, fit a model to the past, assess the impact of vector control. Now, I can now take these models. I have a counterfactual because I've just fitted the evaluated vector control. I do a forecast, both of my scenario, what's happened and what would have happened if I'd done something else. And I have this basis for doing scenario planning. I can now look into the future, make predictions that I can test, and we can do policy. So this is the big vision of error propagation or propagating uncertainty. I had to say that even though I'm out of time. And there's a longer discussion about what we don't know about malaria. I'm going to have to skip over it. So what is adaptive malaria control? Adaptive malaria control is just this: iterative, robust analytics for malaria policy. Now, we've done this with the basics, and over time, we would very much like to add in components to deal with drug resistance, insecticide resistance, and all of the better treatment of entomological data, better treatment of the way we think about antimalarial drug treatment, and all those things. But we have something that's up and running and gets the basics right. So with that, I am going to say another one of the slides that sort of crashed is an acknowledgement slide, and I don't have that. So let me just acknowledge all of my colleagues at the Uganda National Malaria Control Division, Division of Health Information in Uganda. So there's Paul Mbaka, Jimmy Opigo, and their teams. My team in Uganda that I've paid from a Gates grant, John Reck heads it, and that's it's been a terrific team of Ugandans sort of who are now sort of at the point where they can actually do these analytics. And we're doing them right now as the malaria is going under, as the program is going under review. And on the other hand, I have this set of colleagues on the Bioko Island Malaria Elimination Program. And if you look at my CV in Google Scholar or something, you'll see my collaborators. They're very bright. I have a team in Uganda. I have funding from the Malaria National Institutes of Health and National Institutes of Allergies and Infectious Diseases. We'll see in the insane world we live in whether that is sustained, but for now I still have that funding, and I also have had funding that is now ending from the Bill and Melinda Gates Foundation. So gratefully acknowledge all my funders, and if there is time, I will stay around as long as I can to ask or to answer questions. Thanks.
Thank you very much, Dave. Thank you. Great talk. Thank you. Thank you. So, I want to know if there is any question from the online participants, questions from the participants on ground physically. Questions? Dr. Afis, can you help us know the number of people that ask questions? Only one person. We are seeing only one hand.
Two hands up. Okay, so that's the people that wants to have a question from here.
Only one hand, right?
Two hands.
Okay, so can we get people who are interested in asking questions from the online participants? Online participants, any question? Okay, okay. So should we start with online participants? Oluwafemi Oyemakin. Yes, online participants who ask questions, or you want to type your questions on the message platform, chat questions. Okay, so maybe we start with the people on ground physically, and then we come back to the online participant. Go ahead, the first person, ask your question.
Okay. Hello. Thank you, Prof, for the insightful presentation. Can you hear me?
Yeah, we are hearing you.
Okay, all right, thank you. So, yes, thank you. So I really want you to clarify this aspect of nowcasting outbreak identification. In the context of malaria, what do you mean by that? I want you to shed more light on that aspect. Thank you very much.
Should I? So let me just answer that quickly.
He was asking a question on
Oh no, I know what he was asking. In Uganda, we have.
Did you get the question?
Questions and then answers?
Dave, did you get the question?
Should I answer that right now?
Yeah, go ahead, please.
So what I mean is every week, every facility texts some indicators to the central offices in Kampala in Uganda. So there's a weekly reporting system, and then there's a monthly reporting system. The monthly reporting system is more thorough, and that's the backbone of the system. That data comes in on a schedule. We know when it's entered. So in Uganda, it's all collected digitally. So it's entered within a month after it has been collected. It's available to us. We've cleaned it, or we've created the raw, we rerun our algorithms, updated our algorithms, recreated the raw database, rerun our algorithms, recreated a clean data set. And so actually before the month is up, we have a renewed data set, which is our clean malaria data. And we run a set of algorithms on that do outbreak investigation or outbreak identification. So that's what I mean is we're sort of continuously assessing what we think is the present. So the present is not like the past and it's not like the future. It never actually happens. We're always in the present, but we can never identify because the minute we say it, it becomes the past. So it's just what I mean is this short window where I care about what's happening in malaria now. That's what I mean by nowcasting. And the way we do that is we make sure that we have our algorithms are stable and that they're being run routinely every month so that we have a clean, updated picture of what's happening in malaria that we run. And because everything's been done in this pipelined way, we do these standard statistics and we repeat them every month. So that's what I mean by nowcasting. People have done formal Bayesian statistics where you have a longer delay between the data being collected, usually on paper, and then there's a digitization process. We don't really worry about that because, at least in Uganda, because the data are being collected and reported into the system every week or every month. So we just take the data and we interpret it. So that's what I mean. Every month, data come in, get processed. Within a month or within a few weeks, there's actually a schedule for it. It happens very quickly. The data turn back and they're available to the program to be used.
Thank you.
Okay, so next question, please. Next person.
Olu.
Hello.
Can I go ahead?
Yeah.
Can I go ahead, please?
Okay, go ahead. Go ahead.
Okay. Thank you, David, for that brilliant presentation. I joined late, and I thank Professor Bakari for putting this together. I saw it, the invite on the African platform for biomathematicians, and I decided to join to listen in to the discussion. I quite enjoyed your presentation. But my worry is in three phases. Number one, you introduce a software called SIMBA, right? I'd
Yeah.
like to know whether this is available for use now.
Yes.
That's one. Secondly, about 23 OECD nations have eliminated malaria, but it's still endemic in Nigeria. So what is your suggestion? So talking towards elimination science in malaria. And finally, we know that production of vaccine is always it is always at a huge cost. And a lot of models are factored in the use of vaccine. How can surveillance system, be optimized into eliminating this malaria that we're talking about? So these are the three questions that I have worry about. Thank you.
Thanks. All good questions. On the last one, with malaria vaccines, we're struggling with this question right now because Uganda will be rolling out vaccines now in young children. So we're making sure we have the systems in place to track the number of kids who are vaccinated. Sorry, I just want to make sure that I'm not talking over someone. Yeah, so the vaccine surveillance is a very good question that we're working on right now with the NNCD. I don't have a good answer right now. I do think, and particularly the evaluation component is a very serious one. So we need to make sure that we're monitoring and evaluating, collecting the data and analyzing it appropriately. So the second part of your question was actually about malaria elimination in Nigeria. The short answer here is malaria is in sub-Saharan Africa. We have some of the most pernicious vectors that there are anywhere in the world. Now, there's some pretty good vectors in like Madong, Papua New Guinea, and other places, but almost all of South Africa or Southern Africa has one of below the Sahara has one of, Anopheles gambia sensu latu. So it includes one of the Anopheles gambia species complex and Anopheles funestus in some mix, plus other vectors, minor vectors that we don't pay as much attention to because the other ones are so predominant. So we have all of these mosquito species that give us the highest rates of malaria in the world in sub-Saharan Africa, and that's why it's been one of the reasons why it's been so difficult to get rid of it. Now, the other thing I would say in a place like Nigeria is that there are opportunities for doing malaria in a kind of stratified, targeted way where communities can get involved. And I would argue there are very different challenges for eliminating malaria in cities, in urban areas versus rural areas. And some of what I've been very interested in is sort of how that works. But yeah, I do think malaria elimination for a place like Nigeria is going to be much more challenging than it is for a place, further north. And, how do we do it? Well, I mean, one of the things is we sort of start with measuring malaria, using the data to evaluate what's worked and what hasn't, and move on from there. And this is one of the things I'd like to emphasize is this is something Nigerians can and ought to be doing by themselves. They don't actually have to look to big people with big machines somewhere else, right? And the last part of this is SIMBA. So is it available for use? Yes, it is. On the slide, I'm looking at, if you go to David Smith Malaria in Google Scholar, you find me. That links you to my web page, and there's a link that says SIMBA. So if you're still sharing my screen, this is the SIMBA website. SIMBA is a set of 6 now core R packages. If you're interested in using it, write me. Pretty soon we will have some GUI interfaces that'll make it much easier to use, but they're actually well documented. So if you go to RampXDS, for example, this is what you find when you go to the website. Here's RampXDS. Here's how to get started. And then if you look up some of the articles, here's one called Getting Started. It'll walk you through, and building a model it walks you through the parts. so on and so forth. So you can actually teach yourself a lot of this, and if you get stuck in this, it's pretty complicated software because malaria is pretty complicated. We've made it as simple as we could. If you want to use it and you get stuck, you know, if you go back to my web page, you'll find my email address. Write me, and I think it's right at the top. Anyway, I've got other sort of things encroaching on my screen. I don't know why. It's very annoying. But yeah, so the information is there. If you want to use it, yes, you can. We've been working with two mathematicians from Uganda who we found at local universities who have all the skills they need. So, you know, people in Africa have the skills they need to do this kind of thing. We don't, and what they needed was a framework for sort of working interactively with the data. So yeah, that's the kind of thing we need anyway. Yeah, and there was one answer, there was one question on there about, since we're coming to an end, mosquitoes predominantly bite people at night. Does it matter? Yes, it does actually. So when we're trying to look at the effect of malaria control in a place like Bioko Island, we actually have good data on the biting times of mosquitoes, so they bite more at night, but that doesn't mean they're inactive during the day. They are still blood feeding during the day, just at a lower rate. So we have a concept in the models that we developed called time spent, and we pair this with a model of activity, mosquito daily activities, and then we get a model we call time at risk, which is a submodel. And that time at risk model, when you pair this with other nonlinearities, it means that even a little bit of malaria exposure while you're during the day away from home means that you can appear to have a lot of malaria in a place that doesn't have any malaria transmission. And we've written papers about this, so I can tell you more. Anyway, thanks to Johnny for your question.
All right, Prof, thank you so much for that talk, and I really enjoyed it. Yeah, that's quite a huge model there that you showed us, trying to capture every aspect of malaria transmission dynamics, vector dynamics as well, vector ecology, human epidemiology, and the rest of those things that are put there. But I started thinking about the fact that having to get data to calibrate this model, I don't know what challenge are there in calibrating this kind of model, this kind of huge model, given that you know, in some places in Africa, the challenge of data will be the problem. So, sometimes you want to bring in someone to just answer the question you have in mind without necessarily putting all the things that maybe have to do with malaria in its entire form. All right, and then the second one I want to talk about is also this fitting that I'm actually looking at here. So nice, one on the right hand side, the Madi Okulu district. So nice fitting outcome that in here, kind of a high agreement data and the model. So I want to know, did you use seasonality function in this case, or you use exogenous? Is it just exogenous factors that are able to help capture the trend this way, or maybe you have to bring in some seasonality functions to capture the pattern in data? Yeah, thank you. And over.
Thanks. So I'm going to give two very technical answers to that. On the left-hand side, you're seeing the algorithm we use to translate TPR into prevalence. So this is the sort of the biggest indicator we have of how much malaria there is in its seasonal distribution. We've got more research data describing malaria prevalence than any other single metric. And so we can actually build models like this where we impute PFPR. Now, are they accurate is a different question. Our answer to that is, well, we have to get on with it. So let's make predictions that we can test, and then let's go test them. So this is the core of what we're calling adaptive sampling. And so this is on the left-hand side, what you're seeing is essentially a gigantic statistical exercise. Not only statistics, actually, it rests on all of the data processing pipelines that we've created so that we could have the data in order. There's also serious questions about internal consistency checks on the data to make sure your TPR data are giving something right. How do you choose your denominators, yada, yada. We did all that due diligence, which takes us up to the point where we have a PFPR time series from a TPR time series, okay? Now, you might not like some of the aspects of the way we did that. If you went into it, you'd quibble. That's fine. That's what we do, we quibble. But it works, and it makes a prediction that we can use. And then you get the one on the right, and now we're going to fit models to that. So the way we've done that is we decompose our time series into a mean, a seasonal pattern that has a phase. So what is the timing of the peak, of the timing during the year? It also has an amplitude. And we could, if you like a different function than the one we've used, by all means use it. What we've done here is we're using an EIR, putative EIR pattern to force PR directly. And that EIR pattern we've assigned as sort of its mean, its seasonal pattern, and an interannual variability, right? A spline function that gives us I've eliminated it here, but I think you might be able to see it in another one. Anyway, there's a kind, and we can give you some diagnostics, but this works. So you run this, it takes about, it takes a few minutes to run this to fit this time series, but it's not an onerous computational burden. And you get a fitted pattern. So the red is actually model fitted PFPR to the black, which is an output of the algorithm on the left is statistical algorithm that's predicting PFPR. And so I can go in the details if you want to. It has to do with the way we deal with functions, but I also will say that we dealt with it in a flexible way. There's a kind of a generic framework we have for making seasonality functions, trend functions, and the mean. So we view everything as having a mean, a seasonal pattern, and a temporal pattern. And when I say temporal pattern, I mean it's modifying in a multiplicative way. They're all multiplying the things. So those are the things we're fitting when we get to here. Now, this is an EIR forced model. We can also do one where we go all the way back and we have an emergence of adult mosquitoes forcing things in the model. And I would argue that if you're sort of mainly interested in the intensity and seasonality and stability over time of transmission, these are the things that you want to know. So it's our first pass. Do we know mosquito bionomics? Do we know the mix of vectors? No, not yet. We're working towards a system where we can learn those now in real time. That's the whole point of adaptive management. But honestly, we had to work so hard to get up to this point because there was a lot of work to do to make sure that we could sort of process the data and use it. But nothing that we've done is unmodifiable to account for those things. Now, there's some math that makes us comfortable doing this. I could talk you through it, but essentially vectorial capacity and EIR are very, very closely related concepts in every way you can imagine. And we can have those arguments and discussions all we want to, but essentially I'm feeling very, very comfortable about this. Now, there are a lot of things about malaria we don't know, and many of those are more important, I think, than the things that most of the people would talk about. And I would point out that we have done a woeful job of quantifying vector control, things like connecting up the models to actual real descriptions of what the modes of vector control do, to operational measures of that sort of characterize what the program is doing, that gets translated into a measure of coverage. We've done this better with ITNs and IRS, but not necessarily very well with some of the other modes of control, like larval source management. And so there are a lot of things we don't know about a system, but we know the basics like intensity and average intensity and seasonality of transmission, albeit with some degree of uncertainty. So I hope that answers the question, Emmanuel.
Okay, thank you very much for that brilliant talk and answered questions. Yeah, so I don't know if there are still other questions from anyone.
If you have questions, go looking here. This is my website from the University of Washington. I will point out that you can go to all the websites I've talked. There's a lot of them. There's a lot of material here. It's kind of the interface to the ecosystem we've created in these places. And so feel free, and then please feel free to contact me if you have very specific questions about sort of how to use the software. We are very interested in getting people to use the software. Please don't try to do it in isolation and get frustrated. Write us. If it doesn't work, we'll fix it. This is still beta stage software, but it works. It does work. We're using it. It's just that we're using it for our needs. You might need something else and you can get frustrated. Don't do that. Write me. We'll help you get up and using it if you want to.
Thank you very much. So, yeah, thank you. So, all right. In the absence of no other questions, want to appreciate Professor Dave Smith for having us at this time and taking us through the robust malaria analytics for policy. Hopefully, we are going to, hopefully work together on this as time goes by. Thank you very much for your time.
Thank you for having me.
All right, cheers, man.
Cheers.
Ciao, ciao. All right, bye.